Right, so I'm pleased to introduce to you Zico Kolter. Zico was my PhD advisor back at Carnegie Mellon, and he's a super impressive person. In fact, many of you might take a step back when you hear that his lab has over 25 PhD students. And it grows every time I ask him.
Trying to steady state at this point, but
Still
grew by 1 year. It still grew by one this year.
Every year he tells me it's steady state. They don't always grow every. But he's done lots of things. He works at Bosch, and I'm excited to hear what you have.
All right. Well, great. Thanks very much, Eric. And of course, what Eric's not saying is that one of the benefits of, I guess, having a large group is that you can talk about the different things, and people think you're doing a lot of stuff, but really you're just getting a lot of money and funding, and that's how you actually manage to seem like you're doing so much, right? Okay, so I'm going to talk today about, well, first of all, it's great to be here. Thanks everyone for coming. I'm going to talk today about detecting and adapting to domain shifts in machine learning. I think this is a topic that's gathering a lot of interest these days, and we've developed some work in this area that I think is a bit different from sort of standard approaches in this field, and I'm really, really excited about it. So I'll just jump right in to sort of the problem setting and then some of the things we've been working on. Though I should emphasize, I'd rather have this be a bit interactive, so feel free to interrupt. If I can rush these slides if need be at the end. I'd much rather have a discussion and convince you in the first two portions of the talk than like get through all three and have everyone falling asleep. So that's my priorities here, and so react accordingly. All right. So the first slide of any talk like this has to be like the slide about how great deep learning is, but I'm going to boycott this slide because I don't think it's necessary. And more than that, I really, it's a pain to keep up to date. You got to change it every month. I think we all know that things like AlphaFold is cool. Enough said. So what are the challenges that machine learning faces? What is it really bad at right now? Well, one thing that machine learning is really bad at is, in some sense, knowing how well it will work in real scenarios. And so what I mean by this is I'm going to consider this sort of well-known setting here of distribution shift in machine learning. The idea, I think, is probably familiar to most people here, but I'm going to describe it in some formal sense here. So formally speaking, you have some distribution key, which you train your data set on, training classifier on. And you also then evaluate your classifier on some new sample of data drawn from that same distribution, right? And due to the magic of statistics, we can, be pretty confident, right, that our performance on the true distribution, the actual generalized performance on this data, on this distribution, is approximately equal to the test performance, assuming we didn't, violate any, assuming we actually didn't, overfit the test set or peek at it as we developed our method and stuff like that. But then, of course, the challenge is if you go into the world and all of a sudden your distribution changes, how can you get any guarantees about what your thing, how your classifier will actually perform? And the only thing I want to say on this is that, so I'm going to think of D as my in-distribution data and D prime as my out-distribution data. And the only thing that I want to emphasize here on this slide is that this is not some edge case of machine learning. This is also known as every single machine learning system you will ever build and deploy in the real world, right? There is not ever, maybe there are some cases where your data is generated by some, mechanical process or something like that, where it's like a physical system that's genuinely the same at training and test time. But in every real domain, virtually every real domain, you will encounter a different distribution when you are evaluating and deploying your machine learning algorithm than when you are training it and evaluating it on your test set, right? So this is, in my mind, kind of the most critical problem in some sense when it comes to the practical deployment of machine learning. And this is going to motivate the setting that I'm considering throughout this whole talk here. And this setting, it goes by a lot of names, because sometimes it's like the unlabeled distributional shift setting and things like this, but the setting is as follows. We're going to assume that at training time, we have a labeled data set. And we can do whatever we want with that. We can split it into training tests, validation sets, anything else like this. And this is what we call our in-distribution data. Again, I think most people are familiar with this setting. But then at deployment time, we have some new set of data, some new distribution potentially of data. And we only receive unlabeled data from this new distribution, right? So when you're deploying your system, you don't have someone around to label images for you anymore, right? You just have images. And only from these images, from the input sort of data to your system, you want to do something, right? You receive unlabeled data from something else, and you want to know like what do you do about this? So the question is, under the setting, questions I'm going to talk about today are under the setting, can we, first of all, even estimate how well our classifier will perform? So maybe maybe it's going to be worse than on my test data, but can I estimate how well it will work? And then maybe even better, can I actually improve the performance of my classifier on this new distribution without access to the underlying labels, short of labeling my data again and retraining? And I'll say right now, the answer to these questions are no, we can't do this because this problem is not well specified as it is right now, right? It's an ill-defined setting because the OOD setting could be all my labels are flipped from what they are in my distribution data, and therefore I'm going to get, my performance is going to be the opposite of what it is at training time. And what this typically leads to is for us to build assumptions about like the amount of shift that we allow, or some notion of like distributional distance between our target domain and our source domain and things like this, our in-distribution data and our out-distribution data. And I guess the point that the meta point that I want to make in this talk is that I find these approaches, they're fine, but I find them kind of unsatisfying. Because real shifts that we encounter in the world aren't defined by KL divergences being less than epsilon, things like this, right? I don't even know what that really means. Like the distribution of images, that is, a divergence on that space. It's a really weird thing to think about. I know you can use features and all this kind of stuff and, IPMs and things like this, but I still don't like this, right? What I would instead say is that just like the success of deep learning is not itself some sort of fundamental, foundational truth to the world, it's an empirical effect, right? Similarly, I want to start this whole line of work by looking for interesting empirical properties that may be able to help us with this underlying problem. Okay, and that's really going to be the outline for this talk. I'm going to go over 3 groups of papers. I think it's the next slide should highlight that single paper. I'm going to go over the 3 papers we have. We've had them this year at iClear and this year coming up at NERIS on, in some sense, what amount to different things we can do to attempt to solve these two questions. Because in practice, it seems like oftentimes we can improve performance a little bit, or we can at least estimate the performance of some new classifier on out-distribution data for reasons that obviously aren't true, globally, but which are true for the data that we actually encounter in practice. And that's going to be the agenda here. And we're going to go through 3 different examples. One on the disagreement error relationships, one based upon agreement on the line, what we call, and one based upon a technique called test and adaptation using conjugate pseudo labels. And I'll finish with some final thoughts. Okay, so that's the agenda today. As I said, if I don't get through all 3 of those, it's okay. But hopefully I'll get through enough of these things to at least get you excited about some of them. All right, so let's jump into this one. Actually, that citation there should be on this slide. Let's misplace it. Let me start off by talking about a paper we had this past year at iClear on what I think is a very surprising connection between generalization error, and disagreement, meaning how often classifiers disagree with each other. This is actually going to relate only at the very end. Am I going to bring back in OOD data here? I'm going to first, it's sort of a motivating idea, but it raises a really, I think, interesting connection, especially as it relates to data, a quantity you can compute without labels. So to start off with, I'm going to think about a really simple procedure to motivate what I'm talking about here. I'm going to take some data set, in this case, CFAR10, it's a standard deep learning kind of tiny image classification problem. I'm going to train two different, rather than just training one network on it, I'm going to train two different networks on this data. Same architecture, same everything, just two different networks. I'm just going to initialize those networks differently, right? So just different random initializations of the weights. Okay? I'm going to train two networks, and I'm going to look at how often those two networks disagree with each other on their prediction, and I'm going to plot that versus the average error that those two classifiers get on the data set, which are about the same because they're the same classifier. It's trained on different initializations, right? Some difference, but not very much difference. And I'm going to plot that for a bunch of different classifiers here. And something very surprising here happens, which is that the disagreement between these two classifiers tracks very well, not perfectly, but tracks very well their error, their test error. And to be clear, I mean disagreement on the test data and error on the test data. So these are both on the test set that we have here. Yes.
So is every blue point compared to like, so how many classifiers are in the blue point?
So every blue point is two classifiers. Okay. So each point here is two classifiers trained on the same exact data set, so with different initializations. And what I'm showing on the x-axis here is how often they disagree in their predictions. And the y-axis is what their average test error is. So just the average of the two.
You don't have it that 2 points share one.
No, these are all two different ones. In this case, we're going to go back to that and all cross products in a second. But you can also do all cross products here. That works fine.
Sorry, can we just understand the plot more?
Yeah.
Each of the blue points is generated in the same way, like you.
Yes. Just different, I mean, so this could be like a little bit different architecture. So like each of these points, because there's difference in like where they are exactly, they're slightly different like sizes of network, slightly different recipes for training. So each point is trained in a different fashion, but each point has two classifiers trained in the same fashion with different initializations.
The premise is if I were to repeat the training for exactly the same model, just with different random seeds or something, I'd get a very similar point.
Yes, exactly.
Different points are different.
Yeah. And so what's really sort of fascinating here is that this lies close to the line, right? There's this amazing correlation between how often classifiers disagree and how often and what their test error is. And I mean, you could ask, I mean, I think I show this plot, people say, well, is that surprising? And I think it's surprising. So is it actually peculiar or not? And I think it is, right? In my opinion, this is, because I would naively think that if I train two classifiers on the exact same data, they should be very heavily correlated in their predictions. You would think so, right? I mean, they're the same classifiers, the same data you trained it on. You just initialize them differently with different random seeds. We should be able to have a whole bunch of points here, right? Or maybe I guess sitting down here, but still, they should, disagree very infrequently, but still have varying degrees of test error based upon the recipe you use to train them, or like what size architecture it is, whatever. So, and of course, there also are fundamental limits. Like their disagreement can't be more than 2 times their error, right? So like there's a lower bound here they can be, but they can be anywhere in the space. And I would think they should be clustered around here, but they're not. They seem with sort of surprising regularity to actually lie roughly on the line. And you can do this in a bunch, I mean, and sometimes actually the source of randomness almost doesn't matter. So what else you can do is just have the same initial weights, but just order the examples differently in SGD. And you get something very, very similar here. You get essentially points that lie on this line. Yeah, question.
I was asking about the nature of this segment. So,
Yeah.
Is it the case that most of the time one of the classifiers predicts correctly and the other one predicts incorrectly, or on one of these data points that there's this agreement, both classifiers predict incorrectly, but different classifiers?
Yeah, so both can happen. I actually haven't looked at the exact confusion matrix here. My guesses would be that because let's see. So because this is 10 class classifier here, I think just by the and you're getting especially for these ones, CFAR, so you're getting like 93% accuracy, 94% accuracy. I'm betting like the majority would have one class be correct and one wrong, but like this is disagreement, to be clear, is a binary thing, but they can bring any class they want. So because it's 10 class, they can both be wrong, or one can be right and one can be wrong.
Yeah, so I guess my question was, are these data points where there is disagreement on, are these difficult data points where we cannot say anything?
So yes, like there is some connection between the more difficult data points, certainly, and the ones they disagree on more. So there definitely is that sort of general trend where harder data points do have more disagreement, yes. But you sort of like, this isn't really an ensembling thing where like if you add more members, you don't necessarily get better for reasons maybe we'll see in a second, some of the connections here, but that's the basic idea. Okay, so why might this happen? And what can we do? How can this maybe relate back to OOD data? And one of the, to be clear, we don't really know why this happens. I think with a lot of empirical effects and with deep learning, you have to kind of at some point say like, why does it happen? We don't know. This seems weird. And that's actually going to be a frequent trend in a lot of what each of these three sections, I think, has this ultimately as like a stated point here. But there does seem to be actually an interesting connection to what I've talked about several people actually this morning already, which is this property and calibration, which in some sense is not surprising. There's going to be calibration in this thing because calibrated classifiers, they know their own error, right? So if you have like, so let me put it this way. If you had a perfectly calibrated classifier, you would not need to even look at disagreement because you could just ask the classifier, are you going to get this right or wrong? Like, what's the probability it's going to be right? And you could just build this plot. A calibrated classifier knows its own error. So on unlabeled data, it would be able to already predict its own error without the labels, right? That would be very nice. But of course, individual classifiers produced by deep networks are infamously not well calibrated. You have to somehow recalibrate them to get them to be calibrated. But one interesting thing that is true is that seemingly ensembles of deep classifiers are, in many cases, surprisingly well calibrated. And what I mean by that is, if you have some group of classifiers you trained with a deep network and you sort of take their average prediction over all the classifiers, their average hard prediction. So you look at the hard predictions, not their logits or anything like that, but their hard predictions, average of the classifiers, that result is somewhat well calibrated. And we can actually prove in this case a maybe interesting result. I kind of go vacillate about whether this is how much this really informs our understanding of the empirical effect, but it's a result, which says that if we have an ensemble of classifiers produced by H, and H here is, think about H as sort of the class of randomizations you have over classifiers. This would be like our different random initializations, and then randomized differently, then trained by SGD to some amount of performance. If you think about sort of the ensemble classifier, which is just, again, this is think about the binary case here. So this, if H is 0, 1, this would be basically a number between 0 and 1, right? That sort of averages the predictions. If this classifier here is well calibrated, meaning that the prediction that Y is 1, given that this is predicts some probability Q is equal to Q. So on average, in that bin of examples that predict Q, you actually get it right Q% of the time. Then it turns out you can show that the generalization error is equal to the expected disagreement. So if you sample, if this property holds of your ensemble here, then you can show that the expected error of a single hypothesis is equal to the expected disagreement between two hypotheses sampled from that distribution at random. It's actually not that, again, the intuition, I'm not going to go through the details of the proof there. It's in the paper, but it's actually not that. Again, it relates to the fact that calibrated classifiers know their own error. And so because the calibrated classifier knows its own error, it will, in fact, sort of also disagree with itself kind of the proper amount of the time. And that's the basic intuition of the proof. So the thing I will say, though, the thing that I will say is that I think this is interesting and really a fascinating effect in and of itself, but I haven't actually mentioned the problem that I set out with, which is OOD performance, understanding or improving OOD performance. And so connect to that, to connect this, I think I wanted this to
Let me ask maybe like a potentially.
Yes.
Question. But like, I would also expect in this case, the ensemble classifier to be more accurate than the constituent one. So why should I be like looking at the disagreement reason the constituent classifiers rather than like wondering what is the error of the ensemble classifier?
I see, right. So, I mean, so first of all, like ensembling at certain points, this doesn't help anymore, right? Because ensembling calibrated classifiers is like not going to help you that much, right? In many point, in many cases, because like if you're already calibrated ensembling, then like won't help that much more.
Well, if I have two classifiers that are equally accurate but disagree on many points, then I can provably get a more accurate classifier.
No, not all, not necessarily, no, right?
Or
Like,
at least if you care about square error.
yeah, I mean, you can't always do that, right? Like there will be limits there. But I think, I mean, more fundamentally, like I think what we're trying to do here is we are trying to ultimately assess the performance of real classifiers. And yes, it is known that like if you want to squeeze that out last little bit, like yes, you can ensemble things and like improve performance marginally as you go. But I'm more actually curious about the assessment of the performance of classifiers that people actually use and run, which are not always ensembles, right? So I'd rather stick to assessing performance of real classifiers. But what I haven't mentioned yet is anything about OOD data. And the thing I want to emphasize here is that this could all be applied to OOD data, right? Because you could do this same exact thing to get an estimate of the performance of classifiers in exactly my setting I set out with, which is this sort of OOD setting, precisely because, and this is maybe the important point, and this maybe should make this point more clearly, disagreement can be computed without labels. So I've had two classifiers, and if all my classifiers sort of lie on this line here, and I want to get an estimate of the performance of that classifier, I just train two of them instead of just one, look at their disagreement on this new OOD data set, and that gives me an estimate of their performance on it. So I've solved theoretically my problem because I can compute disagreement without labels, and that translates by this argument to an estimate of performance. Yeah, question.
But this seems to talk about averages, while with real data sets, right? You don't get it all at once, right? You get 10.
It's a good question. Yeah, so these are all averages, right? So this is average performance that we're taking here. So this is the the performance average over the entire data set. Now we haven't. What I would say is the following. It seems like we've done tests with like relatively small subsets of this, but you're absolutely right. This applies not on a per example basis, right? Because per example, you either are correct and you're either like here or here, right? There's nothing in between. So all of these things are average effects you see over entire data sets. And I think that's actually still okay, right? Because oftentimes you sort of operate in these like mini batch modes where you're running some classifier, you'll just execute it on a whole bunch of data, and you'll have time to sort of, collect statistics on that data, for a day. And you kind of want to know, like, is my classifier performing much worse than I thought it was at test time, right? That's kind of the mode we're operating in here. You're not going to get like per example notions of, is this example correct or incorrect, right? These are average statistics over the whole data set. Yeah. Okay, so the procedure that I've given you then, if you can trust these things line on line, would in fact give you a way of estimating OOD performance without any labeled data. The problem, though, is that we're kind of deferring the problem here, right? So, so in some sense, like it seems that empirically, this process works with maybe some theoretical backing if you have, if your ensemble of classifiers is well calibrated in some respect, or would the ensemble of classifiers you're creating in your set is or would be well calibrated. But that's just pushing the question back to, are deep ensembles well calibrated or not? And importantly, are they going to be well calibrated on some new distribution of data? And of course, the answer there is maybe, maybe yes, maybe not. And in fact, what this plot here shows is an OOD setting on what's called, or an evaluation of this sort of phenomenon on OOD data. In this case, what's called the PAX data set, which is a data set of like photos, art, cartoons, and sketches. So it's same classes of 7, I think, objects. I'm getting that wrong. In different styles of picture. So again, a photo of like a cat or a dog, an art, a cartoon, or a sketch of these things. And what we see is that there definitely still is some effect here. So this is actually evaluating on the cartoon subset. You know, the shape here shows what we trained on. So of course, if you train on cartoons, you do very well on cartoons. That's expected. And if you, and like pre-training helps also typically when it comes to these sorts of things, if you train on the right source and target. But like if I trained on photos and evaluate on cartoons, I drifted pretty far from this line here, right? I now have this pretty small disagreements within my classifiers here, but pretty high error. This is sort of what I expected originally, because you know these things will turn to the same exact photo data. They're applied to some new data set, and that's all we have. Like they just aren't on this line. And if we were to use our method here that I've described, of just use disagreement as a proxy for error, this would be a really bad estimate of the error. Right? We'd be guessing the error is like in the 20s and it's actually in the 60s, something like this, right? Yeah.
I said this already, but what is pre-training then?
Well, pre-training is just like, do we train these? It's just like, is the classifier pre-trained on some ImageNet data of different types too? So it's like, do we just pre-train on some extra data beforehand? Yeah. Yeah. Yes.
What is OOD here?
Yeah, OOD is, okay, so OOD, yeah, that one I did say. The OOD stands for out of distribution. So that means the new data set from some different distribution. In the case of PACS, for example, the OOD data would be, in this case, oops, one there. The OOD data in this case would be like the cartoon data set if you train on anything but cartoon. Then cartoons are out of distribution compared to what you trained on.
So it's just a train this. It's not really, and so this concept of all these things very elusive.
I mean, yes, but I'm actually going to embrace that elusiveness, right? I just want to say, like, you have a training distribution that's the in distribution data, and then you have something else you test, you evaluate on. I also want to say test on, because you test on the same distribution, usually, that's how you test, train, build classifiers, but you deploy on some elusive other distribution, which could be the same, could be different, whatever. Yeah.
For like the squares where you train
Yes.
photos, do you find that you were more uncalibrated on those predictions than you were on
Yes.
the ones that were on the line?
Yes. So yes, definitely. So practically speaking, when these things work worse, you are also less well calibrated. But you cannot evaluate calibration without labels. So within the setting I'm describing, where you just, all you have is unlabeled data from your source domain, for target domain, your OOD data. There's no way of assessing any of these things, right? So all you can get is disagreements here. Does that mean we're going to have errors here? Maybe. Depends how much shift there is. I don't know. And of course, you can also get a small labeled data set. But then you can do cross validation at that point, right? At that point, you're just doing test error anyway. So we're missing the whole point. So this is a big problem, I would say, for this proposed potential method here, because there's no way to really validate whether it's going to work or not ahead of time from just the data you have in your unlabeled data. Is the question back there?
Yes, yes.
So when you do without the train, does it not start from a different starting point?
Honestly, I wouldn't worry about pre-training. It's just sort of like showing more classifiers. Just means without pre-training just means you just train just on, in this case, like the cartoon, or just on photos. There's no additional data you also bring to the table.
Yeah, but the weights of the network, you have the same and value when you have pre-trained.
Yeah. But I mean, they're not really the same because they've been pre-trained for a while. So like they've been trained in a whole other bit of data. So they're very quickly different weights of the network.
But without pre-training, you start from a random initial form of the weights, right?
Yeah, I think we probably randomly initialized for both these pairs too. I would guess we follow the same procedure. I mean, check that. Like the pre-training thing is here is just to give more versions of the classifier. It's not really that important for this. Yeah.
I mean, I still think it's somewhat important because you see that it seems that without pre-training on like the upper shift is closer to the disagreement line that you expect.
maybe, but I wouldn't read too much into that. This is sort of one example of these things. I mean, and this is also pretty far off too. Like this one says estimates, 40 and it's really like 75. So I wouldn't read too much into
I
that.
just think it's counterintuitive because everyone is just doing pre-train on very big models nowadays. And then
Yeah,
you get the opposite effect that you would expect.
right. So this data set is not one where you can sort of, I mean, we're doing better without pre-training. So like we're doing better here with pre-training. So like you do better with pre-training certainly, right? Like you do better. It's like your test error is lower. But like it's not much lower here. So like you didn't really improve here, but you disagree a lot with pre-training. So like it's become more correlated. I think it's just like it's a bit risky to make too many assumptions here. Yeah. So pre-training might like correlate it more or something like that. And if the data is not like relevant to this task because it doesn't actually improve it, then it moves it more off the line. Here it moves it more on the line. Like maybe you could read that into it, but I think it's a bit touch and go. All right, I'm gonna move on to the next one. Actually, I'm gonna unilaterally because I want to talk about what we actually do, or what an alternative thing we can do is to address this. I think I probably won't get to the last thing, but I can maybe go through it really fast. Okay, so the thing that I want to mention now is that I want to talk about a different, similarly motivated approach, which deals with this exact problem of being able to evaluate whether or not, our estimate is reasonable or not, right? Using, again, only unlabeled data. And as a starting point, and then this is based upon a paper we have coming out this year called Agreement on the Line, Predicting the Performance of Neural Networks Under Distribution Shift. So the starting point for this, for our work here, was another paper by some folks at all over the place, but some several different universities, including Aditi, who's a co-author on our paper as well. But the starting point here is that John Miller et al. Showed the paper from a few years ago that if you look at a whole bunch of different classifiers, so you take a collection of classifiers and plot their in distribution performance. So now both axes here, I'm going to show a lot of plots like this, so it's important what to label what the axes are for all these things. This is a different plot. I'm in this plot showing the in distribution accuracy by classifier plotted versus the out of distribution accuracy. In this case, this was a data set called CFAR, and a data set called saw that before, but a data set called CFAR 10.2. It was like a data set collected that was much like CFAR, but wasn't quite the same. And they found a really interesting property, which again, doesn't seem interesting at first and kind of expected at first, but I think it's actually quite interesting, which is that if you look at the relationship between, for a whole bunch of classifiers, they're in distribution and they're out of distribution performance, there's a very strong linear correlation, which is actually an extremely good thing for deep learning, to be honest, because it was totally possible that we were just blatantly overfitting like all our test sets and all our classifiers, right? So ImageNet has like 50,000 examples. There's probably been 50,000 papers published that use ImageNet. It's very possible we were just tweaking parameters of our network at this point to overfit the ImageNet test set. And if you try it on a new test set, just like ImageNet, it wouldn't have worked very well. Same with CFAR. CFAR is probably even worse, right? Yes, 10,000 examples for CFAR. But it turns out if you collect a brand new data set, just like CFAR as much as they can, oddly enough, performance does drop. So even though we tried to like make CFAR 10.1, 10.2 as close as they could to CFAR, like they still saw a substantial performance drop. But there still remained this like very strong linear correlation, meaning that better performance on this original CFAR test set. I just mentioned that, to be clear, these are all test accuracy. I'm not going to show training accuracy anywhere on this. This is all test performance here. Better performance here correlates pretty well with better performance there, which is like really actually encouraging. It means like all this work we did to tack on classifiers to get like 2%, 1% better performance does seemingly actually translate to new data sets. It's just that you get a drop, sort of a universal kind of drop in performance when you shift distributions. And this is really, I think, a really interesting phenomenon. However, we can't use this for anything like for the setting that I talked about, right? Because to estimate the slope of this line, which was kind of what you need, right? You sort of need to estimate the slope of this line to get an estimate of OOD performance. You have to get a bunch of points on this line, which all require knowing the OOD performance, which requires labeled OOD data. So you can't actually use this from the setting that I described before. Is that a question there? Yeah.
Yeah, have they studied like this correlation on like multiple data sets? Like what's the nature of the, like how does the nature of the outage?
Yeah, so that's a great question. Like what kinds of shift are allowable for this or not? Because of course, this does not have to happen. What they've shown is that for, I mean, a little bit, yes, and there is some theory in like of Gaussian settings too, stuff like that, though. I don't think it's, practically speaking, people don't really know the answer to that question. But I'll actually get to that at the very end of the talk, sort of the nature of shifts and stuff like that. But this happens not on every data set, but on a lot of data sets. So this happens in a lot of cases. I'll show actually an example later where it's much less of a line. That happens sometimes, but it's pretty often like a pretty straight line for these things. Okay, so what we found in our work is that surprisingly, and this again, this is surprising, like it seems like this might be obvious, but it's totally non-obvious and it's very hard to relate these two things, is that a very similar phenomenon happens also with agreement here. And what I mean by that is if I look at, and here I'm unfortunately, my plots are getting a bit confusing here because I want to show that, but the pink point, I want to show multiple different quantities here. But the pink points in this line, what I'm doing is I'm taking a whole collection of classifiers. I am computing their in distribution pairwise agreement on the CFAR10 test set. And then they're out of distribution pairwise agreements on CFAR10, on like the CFAR 10.1. I think this actually, this was 10.1, it's also 10.2, this is 10.1. And to be clear, every point here in our corresponds to sort of like all pairwise comparisons. So we have a collection of n classifiers, we take all n choose 2 combinations, and I'm plotting a pink point here for all n choose 2 combinations. Okay. But the point is that we can compute all of this without labels at all, right? Because we're just looking at the agreement of classifiers in this on my in distribution test set and the agreement of classifiers on my out of distribution test set. And something kind of amazing happens. Well, two things that happen that are kind of amazing. The first is that this also lies on the line. So this we also get this effect here where there's a strong linear correlation between agreement and in distribution agreement and out of distribution agreement. The more maybe practically important thing though is that the slope and intercept of this line for agreement more or less matches the slope and intercept of the line for accuracy. So in fact, the blue dots here, this is why I can't label each axis here, because one of them's agreement and one of them's accuracy. It's unfortunately scaled in the same way. Those are fortunately scaled in the same way for the different quantities. The blue points sort of behind this are the same thing, but with different accuracies. All right, so in distribution accuracy and out of distribution accuracy. And these two, and I'm showing one example here, but in the paper there's a whole section of these plots. We again see that not only do these both lie on a line, they are roughly speaking the same line. And now this is immediately practical. We have a way from this of estimating out of distribution performance. And it's really simple, of course, right? The idea is you use your unlabeled data to estimate. I mean, this actually, we have a slightly more involved procedure. This is sort of the simpler procedure. Use your unlabeled data to just estimate the slope and intercept of this line, right? Just estimate A and B for this line. Take your, once you've estimated those, assume they're the same for accuracy and for agreement, and just plug in the in-distribution accuracy, which you can compute, to get an estimate of the out-of-distribution accuracy. And as far as methods go for estimating performance of classifiers out of distribution, this works surprisingly well. So we compare to a lot of all other methods people have developed for sort of evaluating the performance of classifiers with only unlabeled data. And this winds up, in general, outperforming them. Yes,
I'm gonna ask a question based on a fact I learned from you about an hour ago.
okay,
Okay, so you have this theorem that says if your like ensemble classifier is calibrated on some distribution.
Yeah.
Then the disagreement probability is equal to the.
Yep.
Now you told me about an hour and a half ago, I guess, that empirically by using temperature scaling, you can with only unlabeled data calibrate.
if, what I said was, if temperature scaling can calibrate,
That's right.
then you can calibrate with only
That's
unlabeled
right.
data.
So the empirical thing, I guess, was that often temperature scaling.
Yes, cannot calibrate, yes.
Cannot.
Often temperature scaling cannot calibrate it.
That suggests this alternative thing, and my question is, have you tried it? Like,
Yes, yeah,
if they can't-
so I mean, because temperature scaling does not affect the agreement, like that would actually, the procedure there would be very similar to just using agreement, what you're doing before, and that's this one here. That's basically this thing. Because temperature scaling won't change binary agreement. We're doing that,
Scenario
yes.
where temperature scaling.
Zico,
Yes.
this is
Hey,
Renee.
hey, Renee.
Hey, I was before this slide, I was
Yes.
going to ask you how much of what you were saying was due to CFAR and CFAR
Yes.
10 versus CFAR 10.1.
Okay,
And particularly, my question was because if you read the design of the data set itself,
Yeah,
the
yeah.
CFAR 1 was designed to minimize the out-of-domain distribution shift of the CFAR 10. And so can you comment a little bit more on what out-of-distribution means for each one of these data sets and how the specific data set design might impact your conclusions?
Yeah, so that's a great question. The reality is I don't know if I have a great answer to that. What I will say is that I'm using CFAR because what people know here. We have similar plots, like a whole appendix of plots in the paper, which is on archive right now, so you can go take a look at them. This is not, these phenomena as a whole are not specific to CFAR. I know I am going to show you more CFAR plots in a second, so I apologize for that. I feel I wish I could say that I'm going to show you other things in a second, but this is more than CFAR. I mean, there are a lot of CFAR ones still here. Just easy to do. We have some from the wild data set, which is a data set from Stanford about distribution shift as it happens sort of in the wild, right? Things like this. To be honest, I forget the nature of all of these ones. CFAR 10.1, 10.2 were created as actual separate data sets. These ones here, CFAR 10C, are like synthetic corruptions that are added to the data set to like make it quite a bit worse, actually, but still sort of work. And then ImageNet V2 was created in a similar way, and I actually forget what FMOW and RxRx1 were doing. I remember they were similar added distribution shifts for. There was one here that might, no, I think these are both image data sets. There's one that we have in the final paper on a language data set too, but I don't know if there's I don't know if I can answer the question of like, what is the nature of shift, but I'll get back to the question of nature of shift in a second, actually, or at the very end, because I'm not sure there's a great answer to that, just objectively speaking.
Yeah, I think that's important because if there was a theorem that were to say, this is what out of distribution means, so this is exactly what the nature of the shift, and for that we can analytically prove that there is this linear relationship.
Mm-hmm.
That
So,
would mean it's hard to believe that this would be true no matter what the shift is.
Of course, yeah. So this is sort of the point, right? Is that you can't say anything about shift in general. To be honest, agreement is something we've been struggling to even analyze in simple Gaussian settings, because agreement for two Gaussian classifiers for two sort of linear classifiers for Gaussian data has no closed form solution. It's like an integral of like a 2D Gaussian, which has no closed form solution. So you have to sort of analyze it. It's actually very hard to get sort of we're looking at this now, but we don't have a great theorem here. This is very much an empirical statement.
Great, thank you.
What I will say though is that this does come with a bit of a sanity check, this method. So the nice thing about this, actually I think the best thing about this method is that unlike the previous one, where it could be wrong and you would have no way of knowing whether it was wrong or not, what we see in this method, again, this is an empirical effect, so you can choose to believe it or not believe it, but empirically speaking, it seems like the higher the degree of linear correlation in agreement, the better this estimate is. So when both agreement and accuracy lie on the line, they tend to lie on a very similar line. And so you can do this. When they do not lie on a line, which just happens, this is actually the same kind of thing, but for Gaussian corruption instead of sort of it's like a fog corruption, it's like Gaussian noise added. For whatever reason, they don't lie as much on a line. In this case, either accuracy or agreement. And so it seems at least empirically like we have this if and only if kind of relationship between these two things. Okay. And so that's, I think, kind of a interesting and important property of this method, that you have this sort of built-in sanity check. I think I might go to the last section now, and we'll wrap up. I want to at least mention this one before I finish. So we'll take questions maybe to the end. So that's okay. 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 So the reason why so that last one I think is very compelling because it lets you empirically, for no, I mean, you're not going to be certain about this unless you sort of trust it to a certain extent. But if you trust it, it will tell you both, like, is this estimate going to be accurate? How good is the fit for the line? And if it is a good fit for the line, it seems empirically like you get a pretty good sort of estimate of the out of distribution performance. And by the way, this chart here, maybe it wasn't specific, but this chart here was like the error between the predicted and the actual accuracy. What I'm showing. So lower is better there. Okay, so let me go to the final section here, which is on what do we do about this? Because everything I've been talking about so far has just been about how we improve, how we estimate performance out of distribution, not actually trying to improve upon it. So I'm going to go quickly through this last section because there isn't much time left. But in the time that I have left, I want to mention at least highlight some of the work we've done on trying to improve performance of classifiers in this setting where you have unlabeled data from a new domain. And the starting point here is this method called TENT, test entropy minimization, or test entropy, I think is what TENT stands for. And the idea of TENT is that you take data from your new distribution and you minimize the entropy of the softmax of your predictions. Okay, so there's some details too, like you do this in batches. You also you don't optimize all the model parameters. You only optimize like the batch norm parameters, like the small subset of parameters of your network. But you do this, and it works. Here's the plot showing it works. But why? So you know, like this is your original error. Again, on some corruptions, you minimize entropy of your predictions and works better. Like, this is crazy. Like the rationale they give in the paper is that like the real predictions on in-distribution data have, you know, lower entropy than out of distribution. So we're going to minimize entropy. That seems like weirdly acausal reasoning, right? It's like our predictions are bad, so we're going to make them more certain, and then they're going to be good. But it seems to work, right? Like this seems to oddly actually decrease the out of distribution error on some of these settings here. I can't like describe just how weird it is this thing actually works, but it does appear to actually decrease the error out of distribution. So I found myself like very irritated by TENT. It seemed like just like totally hacky and weird. They just like picked entropy to minimize they're minimizing entropy. Entropy is also, right, it's like a concave function that they're minimizing. It's very, very weird, but it works. And so, you know, I found myself saying, okay, like, look, maybe there is something to minimizing some function of your predictions at test time. But like entropy couldn't possibly be the thing to minimize like that. Why that? They just picked it out of a hat, right? So what we can do instead is just try to meta learn the right function to optimize at test time. Okay, so there's a few little steps that I mean by that, but let me describe what I mean by that. What I mean is we're going to have some function L, which is a function of our hypothesis outputs, right? This is the outputs of our classifier. And we're going to like search with a small labeled data set of out-of-distribution data, but you know, we'll try to generalize over that later. We're going to search for the best function such that when we minimize this function at test time, it reduces our actual addition error as much, or our real sort of test error as much as possible. And it works. So, you know, it's a small kind of, but consistent improvement over tent everywhere. And so, you know, this works great. So we can write a nervous paper about it and everything's good. But before we did that, we said, okay, you know, what is this function we've learned? What did we actually learn here? So this black function here is softmax entropy. It's like, you know, 13% error. And this weird, like jaggedy, but they're jagged because they, you know, parameterized by a ReLU network, or actually parameterized like a transformer or something like that. But it's this function here, right? And the weird thing is if we actually just take entropy, and I mean, I know it's a multidimensional function, but it actually looks pretty similar in all dimensions. So you can roughly represent it as a 1D function. If we just take entropy and just scale it and move it up and down, because again, we're just optimizing it, so the actual offset doesn't matter here. It looks surprisingly similar to what we learned. And actually, not only is it similar, but actually also it's lower error. So like these jaggedy things aren't valuable. They're just like an effect of a ReLU network. So this is crazy, right? We optimize over all possible functions. We Mellon learned over all possible functions. We could optimize the test time. And what we found was tent was doing the right thing, modulo like a temperature scaling. But that's the only difference. So just, I mean, again, temperature scaling, I know it's like the black magic that makes all these things work, but like one parameter, basically we've learned through all, you know, all of 10 plus one parameter you tune seems to be the actual optimal thing to do. And this is incredibly repeatable. So different architectures, different optimizers, different everything, you kept getting this effect. The one thing we could do to change this function, to make it look different, is to change the loss that we train our network with. So if we trained our network instead with squared loss, still a binary classification problem, we just trained it with squared loss, you get like a upside down quadratic instead as your best meta-learned function to optimize. And that's simply the only thing you can do to change this. It's a different loss function. Okay, so what is happening here? And as a common theme, like that goes through a lot of this talk, we don't really know what's happening here. I mean, this is like, even though I'm going to explain one hypothesis about like what could be causing this, which, you know, also makes nice predictions. The reality is, like with all these things, these are empirical effects. We don't really know what's happening. It's like some weird combination of losses and optimization and deep networks that we don't understand in the first place. But we have noticed this really interesting connection here about why classifiers, and I should mention, like these classifiers here were all trained with cross entropy loss, right? That's like a standard way you train classifiers. It gets this softmax entropy kind of term. This was trained with squared loss. This is upside down quadratic function. And the connection that we found deals with a property called the convex conjugate, which seems really almost like too much of a coincidence to be a complete, or too good to be a complete coincidence, though we still don't fully understand this. Okay, so the first thing I want to mention is that most loss functions can be decomposed. So if you have a loss function, this is the picture of the classifier, these are the class labels. Most loss functions really in practice can be decomposed into some function f of just the predictions minus a linear term in the labels, right? So like cross entropy loss, this function here is like the log sum x term, and then minus a linear term in the labels. Squared loss, you just like ignore a constant term. It's like the squared of the hypothesis class minus the a linear term of the labels, right? And this like fact of like a convex function minus a linear function looks very, very similar to the form that comes out when you start talking about convex conjugates of convex functions. So let me just define what that means. And this is, I'm going to go through this quickly. This is like the one, this and the next one are like the most math of the whole talk. But the idea here is that, especially for overparameterized classifiers, you can think of minimizing over your whole set of parameters as effectively, not quite, but almost just minimizing each individual prediction of your classifier over like the hypothesis that you're going to output on that example at training time, right? And because our loss function is the form of a convex function minus a linear term, this winds up being equal to a function called the convex conjugate, actually the negative convex conjugate of yi. And if you look at the optimality conditions associated with the convex conjugate, you can actually plug in the sort of optimality conditions here, which is convex conjugate evaluated at the gradient of this function applied to the hypothesis class. So that's the details aren't really aren't important here. It's just that by kind of where the convex conjugate, like a classical sort of important function kind of related to duality and convex analysis, is basically defined as this thing here. We're minimizing, so it's sort of the opposite of that, but that's the same. It doesn't really matter how you find it. And like when you optimize this to solve for this, you get this optimality condition right here. So this part doesn't really matter. I mean, the details here are somewhat unimportant. But what's really interesting is if you look at this final form here, the convex conjugate for cross entropy loss winds up being that exact softmax entropy term that Penn uses. And the convex conjugate for squared loss winds up being the negative squared loss, which is what we empirically saw happen when we used a quadratic loss. The last thing I'll say here, like the last slide of math, is there's another way to interpret this. Another way to interpret this is that you are plugging in, you're taking your loss function and you're plugging in pseudo labels generated by the optimality conditions of the convex conjugate. So actually, those end up being equivalent. And probably actually you really want to implement it this way if you're going to do that. Just note that like these convex conjugates here, they correspond to like plugging this thing in as the labels of the loss function. Okay, so that's sort of what's important there. And again, the sort of upshot of this is that the same process gives very sort of natural pseudo labels. For example, so what you so let me put this another way. So another way to interpret tent is that tent is taking the softmax output of your classifier. So it's taking like the soft predictors of your classifier, treating those as labels, and then minimizing cross entropy loss like over this set of non-0-1 labels. And that's exactly the same as what Tent is doing. That winds up being equivalent to minimizing cross this entropy function. And another way of generally sort of thinking about this more generic convex conjugate procedure is also by defining pseudo labels based upon this convex function, and this gives a set of pseudo labels. And the point I want to make now is that this in some of this is nice because it recovers Tent and it recovers like the squared loss for these things, but we kind of already knew those things. What's really cool about this is that for any loss function now, you can look at some new loss functions being proposed by whoever's being proposing it. Like for example, this poly loss function that we also just picked out of iClear because we want to find some new loss function. It's also defined in a similar way. And what this formulation gives is it gives kind of the correct pseudo labels to use for test time adaptation based upon your training loss. Right? And what we find, and the details are in our paper, we won't go through that, but what we find is if we consider kind of all possible combinations here, so you know, the original classifier cross entropy loss alone, using Tent, using like poly loss, actually sorry, the original classifier trained with poly loss here, Tent, which is uses entropy, like kind of regardless of how the classifier was trained, using poly loss, which is you know, the actual loss function, but then the pseudo label given by what Penn thinks it should be, versus our final combination here. It often, I mean, again, small amounts. The next one here is the same thing, like domain shift, more in some than in others, but across the board, pretty reliably, using the correct kind of pseudo label that comes out of this convex conjugate winds up being the right thing to do and gives you the best performance. Okay, so I just want to end now with some final thoughts. I think I'm basically out of time, but I want to have one last slide here, talk about the bigger picture. Because I think this actually gets back to it. So what we've shown is a bunch of things each of which I'm actually individually really excited about, right? The connection between disagreement and generalization, disagreement on the line phenomenon, this correct way to adapt labels. But getting back to actually Renee's question about like, what kind of shifts can this actually handle here? I kind of want to start turning this question around. Because I think very often in machine learning, we like to start from first principles and say, okay, what kinds of shifts should I be able to, from some causal model that we have in our heads, if not in our models, what kinds of shifts should I be able to reasonably handle? And I think this sort of first principle categorization of distribution shifts has some limitations. I think it can be quite hard to know how to define what's the right set of possible shifts. Like, when is a distribution really the same versus when has it changed, et cetera. And I think instead, we can start to think about shifts in terms of the empirical phenomena that they lead to. We, but also others, have discovered all these very interesting facts about sort of practical domain shifts that we see in real data, or semi-real data in these cases. And so I would just say, properties like agreement on the line. You could ask the question, like, what shifts lead to that? Or you could ask the question, like, you could define the shifts as having that property or not. And I think, I mean, that's a weird way of going about things, but I think what we could, like, an agenda that we could sort of go head towards, and then of course we want to do both sides here, but an agenda we can head towards is starting to kind of create, in some sense, like a big dependency graph between all of these empirical phenomena, which, by the way, are very useful in and of themselves. I mean, these ones are not that useful in and of themselves. They don't tell you how to do things. Agreement on the line, technical adaptation, et cetera. They tell you what to do with the data. They give you very actionable advice about what to do with these data sets when you want to evaluate performance. Let's think about quantifying distribution shift, not in terms of KL divergence, but in terms of accuracy in the line error, right? Like how far you are for the R squared of the accuracy in the line estimate. And I think that overall, this at least is a good and valuable alternative direction that gives a different perspective under which to consider these things like domain shifts. So that's all I have for now. I think actually I put my website on the end of all my talks. I think actually a lot of senior faculty are really bad at updating my website. So not the last two papers not on there yet, but they're on Google, they're on Archive and they're on Google Scholar. So that's how everyone should really go and find papers anyway.